Hello and welcome to a new episode of Engineering Things. Today, in this next part of the introductory tutorial to PySpice, we're going to be looking at how to run a transient analysis and an AC analysis. But before we go into the coding and PySpice directly, we will first be taking a small step back and booting up LTSpice to help visualize the circuit we're going to be building and get us some outputs so we can anticipate what we're looking for, the kind of results we're looking for. After this, we'll pop onto Atom, the editor, and then I'll start writing up the circuits, and I'll show you how to do a transient analysis, and this will then be followed by a AC analysis, and we'll do some plottings of the outputs as well, such as a just a raw output voltage over time, or perhaps a Bode plot for the AC analysis. So first of all, we're going to head over to LTSpice and get that set up. So here we have an LTSpice circuit, which consists of a voltage source connected to a low-pass filter. On the other side of this low-pass filter, we have a diode, which is acting as a rectifier, and then we have a shunt resistor. So we have three nodes which we can analyze in this circuit. We have the input, N1, we then have the output of the low-pass filter, N2, and then the output of the diode, N3. So first of all, we're just going to run a simple transient analysis. So if I right-click on this, you can see we have a transient analysis where we're stopping after 0.1 seconds. So it's important to point out here that this low-pass filter forms a corner frequency, so we would expect frequencies above this corner frequency to be suppressed. In this case, the corner frequency is about 159 Hertz. So on our voltage source, what I've done here is I've set a voltage amplitude of 1 volt and a frequency of 100 Hertz. So let's just run this. So we've run it. This is our input then. We have the sinusoidal input of 100 Hertz and 1 volt peak to peak, 1 volt amplitude, sorry. And then if we highlight the node N2, so the output of a low pass filter, what we see is there a slight reduction in voltage because it's quite close to the corner frequency, and a slight phase shift. So we'll talk about that more in a second. And then on the other side of the diode, node N3, what we see is that the negative voltages have been rectified, so we only get the positives, so we end up with these bumps. So this is the output of the circuit that we would expect. So very quickly then, I'm just going to switch over to looking at an AC analysis of this circuit. So I'm going to rerun it, and we're just going to look at node 2 for now. And what we see is that the solid blue line is the gain, so it is indeed a low-pass filter, as we expected, and the corner frequency is indeed about 160 Hertz. This dashed line is the phase shift, and what we see is at about 100 Hertz, we have a phase shift of about negative 32 degrees, which is why we had that slight offset of the two wave signals. Okay, so you can see the circuit we're working with here. Now we're going to go over and build this in PySpice and try and replicate the same results. Okay, so we've moved back onto the Atom editor, and we're going to get started with writing some of this Python code to run some PySpice simulations. So first of all, just take note about what we have imported at the top. So we've got the classic NumPy, it's a matplotlib, math, OS. Some of them we're not using yet, but we will get to them. Obviously PySpice and its various packages. We then have set up the logger, and then we have this classic if statement just to make sure if we're running the Windows subsystem Linux or if we're running on Linux, just to make sure that the ngSpice subprocess is selected rather than the shared library which is used on Windows. So I always give a little reminder there. So we're going to go ahead and start making our circuit. So it's going to be a circuit, and we're going to call it tutorial. I spelled that wrong. Tutorial 6. and we're then going to start adding some components. So we're going to start off with just a simple voltage, and we might correct this later on, as we'll see. So this is what we would normally use for a DC voltage. So we're going to connect a voltage source to the input node N1, and then also to the circuit ground. And we're going to give this, just for the sake of it, we're just going to give it 10 volts. Now this doesn't actually matter because we're going to be varying it, so don't worry. Next we're going to add in a resistor. First resistor going between node 1 and node 2. Now I could just copy and paste in some code that I've already got, but I'm hoping that perhaps it's a bit more valuable for you to see me do it so you can follow along. Please let me know in the comments whether it is. If not, I'll just start with the code ready typed out. So we're then going to add so we've added the resistor, we're also going to add our first capacitor. So this is our first capacitor, and the capacitor was between node 2, so the output of the low pass filter, and then the circuit ground. And we're going to give this a value of a unit value of 1 microfarad. And then we're going to do circuit diode, and it's the first diode, and this diode is going between node N2 and the final output node N3. And we're going to use what we've used in a couple of the others. We're going to use a model which is called my diode. And then finally we're going to add that shunt resistor on the output between node 3 and also between the circuit ground. And we're going to give this a 1 unit, so 1 kilo ohm. Okay. Now we do obviously need to define this diode, so I'm not going to bother typing that out. I'm just going to copy it in. So this is a definition for a diode we used previously, and it's the same one we used in LTSpice. So we've written our circuit. So what we could do if we wanted to is we could print our circuit, and we've got no other code there at the moment. So if I just bring over my Windows Subsystem Linux Ubuntu terminal, I can run it and it prints the circuit we've just produced, which is great. So I'm going to move that out of the way for now. So we want to produce a simulator. So to do that, we need to produce our simulator, and it's going to be a circuit simulator, and we're going to set the temperature to 25, and then we're going to set the nominal temperature also to 25. Now if we were to do, let's do a quick recap of a DC simulation. So we would have an analysis output from the simulator doing a DC analysis, and we want the input voltage, so V, and then the name of the input, so V input in this case, and we might do, say, a slice between -3 volts to 3 volts with an interval of 0.1. So I'm just going to copy in a plotter. So this produces an analysis, and what we can do is we can just plot the voltage on node 1 against the voltage on node 2, and then we can also plot the voltage on node 1 versus voltage on node 3. So node 1 is the input sweep in this case. And what we're going to do is we're going to save this output. So this then is what we've done previously. So this is our this is just a DC sweep that we've done. So a series of DC op-amp operational and point analyses. So we can see basically the output is just the rectifying diode. So great. But that's not what we want to do. So had a little recap there. What we actually want to do to begin with is we want to do a, let's just get rid of this. We actually want to do a transient analysis. So to do this, we produce our analysis output again. Analysis, and then this equals a simulator, but this time, rather than a DC simulator, it's a transient. Just need to make sure my spelling is correct. And we're going to set a step time, for example. Step time, and this is going to equal 0.0001, for example, and we want an end time, and we're going to use the same end time as in the LTSpice of 0.1. Brilliant. So we can do exactly the same. We can extract some values from this. So again, I'm just going to copy and paste these in now. So what we can do here is we can actually print out, for example, the outputs on node 1, the outputs on node 2, and now we have this additional output variable in the analysis which we can access, this additional attribute called time. So because we're sweeping across a time. So if we run this now, we can see that we have yes, so we can see that on node 1 we have 10 volts, 10 volts, 10 volts, 10 volts. That's not unexpected. Node 2 again has the same voltage, and then the time values, we do actually have this sweep of time values, which is great. However, obviously we're not using we don't want a static input voltage anymore. We actually want an AC input voltage. So this circuit voltage, that's just a DC voltage input. Now that's not what we want. So we actually want to go back, and we're going to not use a static voltage. Instead, what we're going to do, let's just delete it for now. Instead, what we're going to do is we're going to use a new circuit component, which we haven't been introduced to yet, and that is a sinusoidal voltage source. Okay. Unlike before, we have we're going to label it as the input voltage source. We're going to connect it from the input node at node 1 to circuit ground. But this time we also need to define some additional properties. So we're going to define the amplitude. Oops, sorry. And the amplitude is going to be 1 unit of voltage. And we're also going to define the frequency. And we're going to define that as 100 units of hertz. So now if we run this, we can see the values are no longer consistent at 10 volts, they do change. But obviously just looking at these arrays isn't very useful. So we're gonna plot these, and I do actually have a bit of code which we can use to plot them. So I'm producing a figure, and I'm plotting the time versus the output voltage on all 3 of the nodes. So, and then we're going to save this figure to a file. So let's run it. And then if we look at that output file, what we find is that we do indeed have the same graph that we got from inside LTSpice. So we have the voltage on each of the nodes. Now, something else we can do is, rather than using a fixed endpoint on our time, we can actually relate it to the frequency of the sinusoidal input voltage source. So what we can do is we can actually assign a name, so let's just call it VAC, it could be any variable name, to the sinusoidal voltage source. And then using this, we can reference some properties about this component. So rather than using a end time of 0.01, we could use the end time could equal VAC and then the period of VAC. And then rather than using an arbitrary step time, we could say, well, let the step time be 1,000th of the period. So if we go back and run this, go back to the output, we now see we're only looking at the outputs for a single period of the sinusoidal input, which may or may not be a useful thing to do. But it gives you a lot more options in how you can present the work. Now, we've considered how to do a transient analysis, so we're going to be moving on now to looking at how to perform a AC analysis within PySpice. So let's have a quick look at how we might run a AC analysis within PySpice. So, very similar principle. What we're going to do is we're going to have an AC analysis, and again we're going to produce that analysis output, and as you guess, probably the simulator is not a DC, it's not a transient, it's an AC, so it's a .AC. And again, we need to define some properties. So we want to define the start frequency, start frequency, and that is 1 unit of hertz in this case. We then have a stop frequency, which we're going to set to just 1, say, megahertz, for example. And then we're going to use a decade. So we're going to use a variation, and it's going to be dec. We're doing because we want to sweep across the frequencies, so we're going to do that in a decade format. So logarithmically, I guess, is how we're going to plot it on the Bode graph in a second. And the number of points per decade is going to be 10. Okay. So, what next? Well, let's just print out some things again. So I've just copied this in. So again, we're going to print out the outputs on node 1, node 2, and we're going to print out the frequency values as well, which we can access in a very similar manner to time. It's analysis.frequency, and we've got to make sure that we format these as a numpy array. So let's bring this up. I have misspelled something. Variation, there we go. And here we go. So we can see that we are sweeping across the frequencies, and we can see that we have some output values. So the inputs are constant, so the frequencies are constant, the input voltage, but what we see is these are now quoted in imaginary values, and that's because obviously the voltages are now imaginary because we're looking at AC, we have changing phases and all the rest of it. But again, this isn't very useful to look at, so we want to visualize these results. Now, fortunately, there's actually an inbuilt function that can be used to do this. So if we go up to the top, we can actually import a tool to plot a Bode plot, which is what we had on LTSpice. So from PySpice plot Bode diagram, we can import Bode diagram. And again, I'm not going to bother writing out all the text, but what we can do is just copy and paste something I've prepared earlier. So this incorporates the calculation of a break frequency, which is just the corner frequency in this case, and then we have the Bode. We're then using this Bode diagram to produce it. So you can see the frequency is defined as analysis.frequency. We've then got the we're then plotting the various node output, the node 2 outputs in this case. Now, and then we're plotting the break frequency as just a vertical red line. Now, something you'll notice here is that I've actually indexed r.resistance, and it's flagging a warning because this doesn't mean anything right now. And what we can do is we can go back up and we can actually name these resistors something. So we could call this first resistor R, and we could call the capacitor C. So this now is the resistor and capacitor made up in our low pass filter. So then rather than remembering, oh, it's 1 kilo ohm, we can actually just say we can index R, and we can do R.resistance and then C.capacitance, and that we can use those values to calculate the break frequency. So we can assign these components variable names and then use them to extract values. So we've got all this, so let's try and run it. There we go. Sorry, I hadn't saved it. So let's try and run it again. And we have a little issue. Okay, no, that's actually just a depreciation warning, so it's working fine. Don't worry about that. But what we need to make sure we do is save it to the output. We can run it. We can see it's now pre-printing the break frequency, which is indeed 159.2 Hertz, about 160 Hertz, as we previously mentioned. And if we go on over to the diagram that we're saving it to, the figure we're saving to a PNG, we can see we get this Bode plot. And we're already so we've got the gain at the top and the phase at the bottom. So this is exactly what we would expect. So we've managed to recreate our LTSpice functionality within PySpice, except obviously we have significantly more flexibility within PySpice because we can save those outputs very easily to a file. We can save the figures incredibly easily. So much more flexibility. So this is just a very brief introduction on how to use a DC simulation, a transient simulation, and finally an AC simulation, or analysis, sorry. So I hope this has been useful. If so, please give it a like and consider subscribing. I hope to continue putting out some more tutorials, and I'll catch you in the next one.